Okay, in this video, I'm just going to quickly run through the solutions that I have for the three test one reviews. Feel free to pause and replay parts of this video as needed to give you enough time to copy down the solutions if you didn't already have them. Or you can also pause the video and try to work through these problems on your own and see if your solutions end up matching what I have as well. So we've already talked about a few of these on review number one. The right triangle was provided. It's laying on its side where the hypotenuse is on the bottom here. We were asked to find the values of three trig functions, but I think for this exam, I'm going to ask for all six. That's more indicative of a college level trig student. For number two, same sort of thing. We give you a cosine with two side lengths, ratio of cosine quantity. So we can use those side lengths to identify the missing side length and identify the remaining trig functions. Now this problem does say the trig function values for sine and tangent, but also be prepared for the three reciprocal functions as well. Finally, we did talk about the cube problem in that we found the length of the diagonal, but we ended up not calculating the angle theta to make that work. Now, the initial thought might be that this is a 45-degree angle because we're dealing with a cube and all the side lengths are a cube. But let's recall that tangent of theta is describing our opposite side length divided by hypotenuse. I'm sorry, opposite side length divided by adjacent side length. So in this triangle that's wedged in the corner here, we have a theta value down here, and the opposite side length ends up being 1, the adjacent side length being root 2, then theta would be equal to the inverse tangent or arctangent of 1 divided by root 2. Now this question showed up on a no calculator portion of the test, so I would leave that answer exactly as it is. We can't compute that without a calculator since this is not a pair of positions that we know from our unit circle. When we switch to calculator permitted, we mentioned that with the sine function here equaling 0.45, we can treat that as a fraction, 45 over 100. And set up and solve for the missing side length of a right triangle. That would allow us then to find tangent theta, side length ratio being opposite side length divided by adjacent side length. Looks like I've got a bit of a typo here. I don't know if this is 7519 or if it's supposed to be 79 or 7579, but you can check that on your own with your calculator. For number 5, we have to solve the right triangle. Finding the missing side length is pretty easy to do with the Pythagorean equation, but finding the missing angle measures can be a little bit more tricky. I elected to use tangent, although other trig functions are permitted. Tangent of angle A would be equal to 39 over 80, opposite divided by adjacent. So then tangent inverse of 39 over 80 from our calculator gives us our decimal result. We can trust the calculator on this one since we're solving a triangle. However, we almost never trust the calculator exclusively for solving angles within a unit circle. There's usually more than one solution to those. So we have to have our unit circle understanding to answer those questions. For these triangles, though, this is perfectly fine. Now that I have angle A along with angle C, I could subtract those from 180 to find angle B, or since my calculator was already set up for it, I can use tangent inverse of 80 over 39 to find angle B, because with angle B, the opposite side length is 80, with the adjacent side length being 39. Now we have all 6 components, the 3 side lengths and angle measures. That triangle is solved. We talked about the setup to this particular question in class. So with this word problem, we know the radius of the planet. We know the angle at which we're observing the planet from this passing satellite. We can set up a right triangle and solve for missing components. What I recognized here is that the opposite side length was 43,000 and the hypotenuse length is what we're looking for here. So rather than using sine being opposite over hypotenuse, I chose cosecant because we have hypotenuse over adjacent. That just makes solving for h a little bit easier. Now h is going to be whatever the result of 43,000 times cosecant of 28.85 degrees is, but I didn't actually compute that ahead of time. I'm waiting until the very last step to compute that in my calculator. I know that the distance that the satellite is from the surface of the planet would be whatever the total H quantity minus 43,000 miles is. So I let the calculator do the math all in one step. 43,000 times cosecant 28.85 minus 43,000 ends up being 46,115. So the distance that the satellite is from the surface is approximately 46,000 miles. And for question 7 on the review number 1, we again have this oblique triangle where we're trying to solve for side length D. What I found helpful was recreating a right triangle with the height of the lighthouse being 60 meters. If the height of the lighthouse is 60 and we're looking down at a 45-degree angle, then this total distance is also 60. And so we can find that the hypotenuse side length of the whole thing being the square root of 7,200, whatever that comes out to be. If I know that this side length is 7,200 and I'm looking for this side length D, and I have these angles here, 45 and arguably 120, because that's the supplement to the 60-degree angle that's down below. We could then identify this as an angle side angle triangle, use the law of sines to solve. So the distance D is what we're looking for. So sine of 15 over distance D is one of our fractions, but then we need this key fraction here where sine of 120 and side length of square root of 7,200 is necessary. The side length opposite of a known angle measure is necessary for our key fraction. From here we can cross multiply root 7,200 times sine 15, then divide by sine of 120, making sure that our calculator is in degree mode, and we find that the distance between those two ships is 25 meters. Now, I quickly glossed over how I landed on the 120-degree value here, but let me just remind you that this horizontal line of view is parallel to the ocean surface here. So we have alternate interior angles. That's where the 45s came from. 45-degree angle of decline is the same as the 45-degree angle of elevation down here. And then also, since this distance or difference between the two observation lines was 15 degrees, 15 and 45 make 60. The sum of the three interior angles have to be 180, and that's where the 120 came from. And then finally, we talked about this one in class where we had the two people standing on either side of a tower. We recognize that this is also an angle side angle triangle. So with the angle side angle triangle, 50, 25, and this green angle have to add up to 180. The green angle and this opposite side length ends up creating our key fraction. And then we can use either of the other angles to solve. I chose the 50-degree angle so that we can calculate this side length. With the law of sines, we found the diagonal side length here of the right triangle that's embedded in this position. Now that we have that hypotenuse side length, we could solve. Well, I guess we could solve this a couple different ways. In my mind, and I think in class, we said, well, once we have the hypotenuse and this angle measure here, theta, we can solve for the opposite side length, h, by using just simple sine computations. If I'm looking at my work here, which I did last year, I ended up switching to law of sines to solve this triangle, which is fine. I mean, we have an angle side angle right triangle, but the fact that this is a right triangle, assuming the tower was built vertically, I think it would be easier just to use regular SOHCAHTOA or right triangle trigonometry to find h. So I'll leave that up to you. If you want to use right triangle trigonometry, you should be able to get the height, the opposite side from this angle, to be 335 feet. But you'll notice that I used the law of sines with angle measure here being 90 and the opposite side length being the quantity that we just computed from the step prior. Okay, moving on to the review number 2. Again, we talked about these in class. The question asks us to indicate where the angle is located. So we don't have to be perfect on this, but we should get pretty close. 150, -45, and 600. The additional instructions did ask us to indicate the direction of rotation from the initial to terminal side. So we always start along the positive x-axis. We recall that. But let's also indicate with these arrows, including extra loops if it takes more than one rotation, but use these arrows to indicate the direction that we would rotate to land at that terminal side. For the angle measures that are coterminal with the given information, we're asking for one positive and one negative coterminal angle. So what I like to see here is that a student would mark where that position, 2 pi over 3, is, and then show the math or provide some indication on how you recognize that an additional rotation in the positive direction puts us in a coterminal position where we're reporting this as a positive angle. But from that position, going counterclockwise with a negative rotation, subtracting that one time, we land in the exact same position, but with a negative angle measure. And we repeated that technique with each of these angles here, and you ought to be able to do so with angle measures that are provided in degrees as well as radians. For number 5 and 6, we recognize where tangent or sine in this case are positive or negative. I'm using that the bottom 4 lines on our unit circle quiz to remember where this occurs. Tangent is always positive in the first quadrant and third quadrant. Sine is always positive in the first and second quadrant, so sine must be negative in the third and fourth. So the overlapping position where tangent's positive, yellow, and where sine is negative, blue, they overlap here in quadrant 3. So we know that if we get a tangent result to be positive and a sine result to be negative, then the angle itself must be in quadrant 3, somewhere between 180 and 270 degrees. Similarly, we would approach the same way for questions 6 and 7. Sine is positive and cosine is negative in these regions. The point that they overlap is here, quadrant 2. And for number 7, the point where they overlap is again quadrant 3. With number 8, again, my recommendation is to show a simple unit circle, and if we're trying to find all the positions that satisfy this equation, well, there are 2 spots where cosine is equal to 1/2. There are 2 spots where an x value in the unit circle is equal to a positive 1/2. That occurs at this position close to vertical in the first quadrant, and this position close to vertical in the fourth quadrant. These 2 angles are located at 60 and 30 degrees, or 300 degrees. Those are the 2 numbers that I would report since they exist between 0 and 360. I would not call this angle down here -60. Even though that's coterminal, the number -60 does not fall within the domain of this particular question. With number 9, same sort of thing. Where are the y values equal to -√3/2? Well, that occurs in 2 positions, both close to vertical in the third and fourth quadrant at 240 and 300 degrees. For number 10, this one's kind of interesting. We would answer it the same way, but it's a little bit tricky. You have to recall that with cotangent or tangent, we sometimes get these strange answers. Negative radical 3, for example, could be considered as -√3/1. But √3/1 could also be considered as √3/2 divided by 1/2. Now that gives us our x and y coordinates to consider. Where would x be negative while y is positive? A negative √3/2 x value with a positive 1/2 y value exists right here. But also, since there's only one negative sign in this problem, we could have written that down below here as well. So √3/2 positive with a 1/2 negative indicates this position. And while these 2 numbers are equivalent to each other, they do end up generating 2 different positions in the unit circle, and we have to report both of those, the 150 degree and the 330 degree position. With number 11, make sure that your calculator's in degree mode for this problem. Our job is to find the coordinates of point P. Well, the x-coordinate of point P is cosine of the angle measure, and the y-coordinate is sine of the angle measure. This is a calc-permitted problem because 250 is not an angle measure that we memorized in our unit circle. So for cosine of 250, we get a result of negative 0.34, and for sine, we get negative 0.93. And that to me makes sense. Even though this sketch probably isn't perfect, that does kind of look like the x value is 3/10 of a unit to the left, while it's 9/10 of a unit below the origin. For question B, just kind of an extension, if I'm thinking about the sine quantity at this position, that's the y coordinate at this position, there is another position that has the exact same y value, and we've got to establish what angle that ends up being. So if we consider this position over here, let's see if I can turn my line tool back on. If I come over here to this side, the mirror image across the y-axis, the point at this position also has the same y coordinate here, so therefore it would have the same y or same sine computation as 250. So the instruction is asking for us to find the angle where the sine quantity would be the same. And so the angle where the sine quantity would be the same would be at 290 degrees. For cosine, we're asking about the x-coordinate. Where would it be the same? And again, similarly, the x-coordinate here is this negative 0.34. But if I come to this position in the second quadrant, this position also has the same x value, so it has the same cosine quantity. And this position is at 110 degrees. Now I'm getting those two, 290 and 110, by recognizing the reference angles. This position is 20 degrees off of vertical, but 70 degrees below horizontal. And so when we identify these new positions, this one's 70 degrees above horizontal, and this one would have been 20 degrees to the right, if you will, of vertical. And so 20 degrees beyond 270 is 290, 70 degrees less than 180 is 110. For this last example, we have tangent. What other position has the same tangent quantity? We learned this in physics class, that when we have the same tangent quantity, we're always 180 degrees apart. This is that discussion on resultant and equilibrant vectors. They always point opposite of each other. So the angle measure in this opposite position, 20 degrees off of vertical or 70 degrees above horizontal, lands us at 70 degrees inside our unit circle. For number 12, this is another law of sines problem. What's kind of interesting here is that you've got to imagine how the triangle would be created. We have the solar panel that's 8 feet long, and it's oriented at an angle 30 degrees above horizontal. So at first that seems insufficient to create a complete triangle, but if we recognize that a straight line drawn from the peak of this panel to the base of this panel, this is where the sunlight would be directed. The shadow, if you will, at this 45-degree sunlight, the shadow would occlude the base of this solar panel. So that's where the 45-degree angle comes from here. We have this notion of alternate interior angles again. Or I'm sorry, same side interior angles on this one, 45 and 45. Alternate interior would be the 30 and the 30. But with the 45 located here at this base and the 30 here, we can establish 105 as the missing angle in this position. Again, we can use law of sines because we have the key fraction with a 45-degree angle and the 8-foot length. We can use the 105-degree angle along with side length x to solve for the missing side length x, and that appears to be about 11 feet. So if we were going to organize a solar panel array or a field of solar panels, and we were going to mount them at a 30-degree position, we want to make sure that we space the base of those at around 11 feet apart. Number 13 is real similar to one of the questions we saw in review number 1, except this time the antenna is mounted on a hill. So what's important to recognize here is that the horizontal line is consistent, and if the hill is a 5-degree angle above horizontal, then the interior angle of this left side triangle ends up being 95, while the interior angle of this right side triangle ends up being 85. So 5 degrees less than perpendicular, 5 degrees more than perpendicular. And if we consider that as generating two separate triangles, sorry, my drawing isn't great. I don't have my pen with me. But if I consider my two triangles separate here, then each one individually can be solved using the law of cosines because we have side angle side. side length, angle, side length, and then side length, angle, side length again. And we can have ourselves a law of cosines method to solve for those two triangles. We're looking for length G1 and G2. We call those guy wires to help support the vertical antenna. So G1, G2 set up almost the exact same way. Only modification is the included angle measure between the two side lengths. Okay, pushing on. We're making good time here, 10 minutes per review. We'll go ahead and wrap up this review, hopefully in the next 10 minutes, covering review part 3. Now this one looks like to be the exact same question we saw in review number 1, finding the side length ratios based on some given side lengths. Again, the only discrepancy here or challenging part might be that the triangle is drawn out of an atypical orientation. But we have all 3 side lengths, so we should be able to identify all 6 trig ratios. With number 2, very similar to what we've seen in the past, 8, 17 opposite and hypotenuse side lengths. These are one of the Pythagorean triples that I would hope that you have memorized by now. But if not, you can still use the Pythagorean equation to solve for that missing side length. And I don't believe these numbers are too large for us to do without a calculator. That's why this question shows up on the no calc portion of the review. You can calculate 7 squared and 8 squared and the square root of 225 without a calculator as a college student. Now, answering question 3, this is us solving for trig ratios without the use of a calculator. And so let's remember the inverse of a trig function must be evaluated at a side length ratio to produce an angle measure. So we're asking effectively with this question, where in the unit circle do we have a y value equal to -1? Well, that only occurs here at the base of our unit circle, and that position of the unit circle is the 270 degree position, or if the question was indicated in radians or requested a result in radians, we would say 3 pi over 2. On a question like B, however, there's more than one answer. Where is there an x value that's equal to -1/2? Well, that occurs twice, this position and this position. Since there's no other specification here, we don't know which one to report, so we have to report both of them. And so the position here in the second quadrant is 120 degrees. Here in the third quadrant is 240. And when we report those as radians, we'll call them 2 pi over 3 and 4 pi over 3. For question C, let's see if I can slide over here. For question C, same thing, only this time the ratio is written in a kind of a strange way. Hopefully you've seen enough of these by now to recognize that root 3 over 3 is the rationalized form of 1 over root 3. 1 over root 3 could also be written as a half over root 3 over 2. So the position where we have one positive and one negative x and y coordinate, where the y coordinate is, oops, and I think I spotted a mistake here. For the tangent function, we want the y coordinate to be 1/2, but the x coordinate to be 3/2. So that's not these two positions here at all, is it? Let me see if I can correct that. So the y coordinate of a half is here, and the x coordinate, I'm sorry, and another y coordinate of a half is down here, while the x coordinate is root 3 over 2 and root 3 over 2. So positive y here with a negative x would give us the negative result. A positive x but a negative y here gives us the same result too. So I don't like 120 and 240 as the answer. I actually like 150 and 300. So be careful there. 150 and 300, oops, appear to be the correct answers. And then if we were to report those as radians, we'd have 5 pi over 6 and 11 pi over 6. So hopefully you don't make that mistake. And for those of you that did work on this review, hopefully you recognize the mistake and were prepared to let me know about it. Okay, so moving on. There's a unit circle that was going to be part of our exam, but we've taken that quiz enough that we don't need to put that into the exam itself. Here's another question about positions, finding a coordinate on a unit circle. This time these angles again are not well known, they're not memorized, so we have to use a calculator to identify them. So cosine of 310 gives me the x-coordinate, sine of 310 gives me the y-coordinate. And again, in a similar fashion, if I'm looking for an angle with the same cosine as 310, that means what other angle, in this case I labeled it as I, what other angle has the same x value as 310? Well, that's at the 50-degree position, because 310 is 50 degrees off of horizontal here. This position is 50 degrees off of horizontal up here. For sine, the same y value, well, jump across the y-axis, looking at point 2. That's 230 degrees, 230 degrees. And then finally, position 3, 180 degrees, the opposite. Equilibrant and resultant vectors from our physics class help us see that as well. But the x and y division here, both are one positive and one negative, leads us to an x and y position here, one positive and one negative. So the tangent computation ends up being the same. With number 7, it's basically the same question as this, we just don't give you a picture this time. So find all angles between 0 and 360 that satisfy this equation. Well, we need cosine inverse of negative 0.1. You can think of this as a unit circle problem in that 0.1 is the adjacent side divided by hypotenuse, so we can think of this as just negative 1 over 10. But the problem is that doesn't really give us the position in degrees, so we would need a calculator to find that. Now the calculator does spit back an answer when you use cosine inverse, it's 95 degrees, but we also have to recognize that we want all of the angles between 0 and 360. This 95 degree position is only one of them. So the other position that has the same x coordinate as this would be down below, and this angle down below is 95 degrees below horizontal. While, I'm sorry, let me say that again. 95 degrees below this horizontal, while this one was 95 degrees above that horizontal. So 95 less than 360 ends up being 264. And we got the answers accurate to several decimals because the calculator was able to compute that for us. For question number 8, it's done the exact same way. We just want to put our calculator into radian mode since the instructions did say so. We have again another law of sines or law of cosines problem. This time we're asking you to solve the triangle in its entirety. So I like the law of cosines here because we have a side angle side triangle, and we can use the law of cosines to solve for a missing angle measure. In this case I solved for A first, but then I abandoned the law of cosines to solve for angle, whoops, should be angle C. I have that labeled incorrectly here. Label this C instead. Angle C was easy to find because we know the sum of the angles ends up being the difference between 180 and the existing angles. So we just subtracted them from 180. For question 10, here we have a side angle triangle. So that usually leads us to believe we have an ambiguous problem, but since the diagram was provided, we can trust that the triangle is complete. It is possible. So rather than concerning ourselves with the ambiguous case and testing for hypotenuse lengths and that sort of thing, we'll just use the calculator and allow it to display a result back to us. Fortunately, the result for the angle B and angle A being 45 degrees and 59 degrees, while they're not perfect, they don't seem too unreasonable. This one may or may not appear to be 45 degrees to you, but it's close enough. I'm happy with these as an answer. They seem representative. Moreover, the side lengths appear to be representative as well. Side length A being the smallest value, B being the middle, and C being the longest side. They correspond to the angle measures and their sizes as well. Lastly, number 11, this is kind of a bonus question that I was considering. If we took the square problem or a hexagon problem from discussion in class and went a little bit farther with it and turned it into a octagon, could you find the, if you want to call it the diameter, I think we call this the apothem. Oh, no, that's something different. If we wanted to measure the length across the diagonals here, we wouldn't call that diameter. Now I'm Now I'm at a loss for words because I can't remember what it's called. The apothem measures from the center to the perpendicular side, or perpendicular to the side in this position. So it's kind of like the radius, but that's not what we're looking for here either. Anyway, if we're looking for side length C, one could recall a rule from geometry class, how to find the interior angles of a regular polygon. In this case, an octagon has an interior angle measure of 135 degrees. Since that's 135 and the straight line connection between this point and this point creates an isosceles triangle, we can establish that the side or the angle measure in each of these corners is 22.5 degrees. And with those angle measures and the side lengths being 1, we can set up a law of sines or law of cosine situation. In this case, I ended up using law of cosines to find this side length in blue. That's kind of tricky. It's the square root of 2 plus the square root of 2. So that's kind of interesting. But if we took that side length along with another one within the problem here, we now created an isosceles right triangle inside of the octagon. And we've established the length to be this quantity here after using the Pythagorean equation. So after I completed the work in blue, I got to thinking, well, what if you had focused on this particular triangle here in pink? And I believe you can solve it in a couple fewer steps, but by identifying this angle measure down here or up here, you can solve the hypotenuse of that pink triangle with that particular setup. I didn't show it here in this review, though, so I'm going to leave that as it is. So I know that video was a little bit lengthy. Thank you for paying attention and participating along with it. I hope that helps you understand some of these problems. We will go ahead and go forward with the exam tomorrow, Wednesday in class, even though I didn't see you today on Tuesday. We've had enough review and we can't delay this any longer. So please email me today if you have questions. That's the best way to reach me while we're away from school, and I will see you tomorrow. Thanks for watching.